All right, so we looked at how polar coordinates work and polar equations, compared them to their Cartesian counterparts. And now let's look at curves in polar coordinates. So let's see here. Let's come right over here to here. All right, so the first thing I want to look at are circles. And you need to know the forms and be able to recognize them. What I'm going to do is I'm going to illustrate a lot of this in Desmos. So I'll leave it to you to come in here and draw examples possibly if you want. But let's go over to Desmos and look at what these circles are. So open up Desmos here. So one of the nice things about Desmos is you could actually have a nice grid like so. And so if I wrote r equals 5, for example, there's a circle of radius 5. I wrote r equals c. That's a bummer. I want it to give me a slider. Oh well. So r equals a constant. We know that that's a circle. What about r equals a cosine t? Let's call it t. Well, I'm going to add a slider here. And, oh, whoops, sorry, not t. We want to call it theta. Then it knows what we're doing. All right. And so look what we have. This is still a circle. But notice that it's oriented differently, right? It's not oriented, it's not centered around the origin. It's sitting along, right, the x-axis here. Its center sits on the x-axis. And notice what happens when I change the values of a, right? Larger a's in magnitude create larger circle. And if a gets negative, then the thing sits with its center on the negative x-axis, okay? What if I change this to sine theta and spelled it correctly? That would help. Well, as you may have guessed, that will sit on the y-axis. Excuse me. And so there's our circles, okay? So let me jump back over here. And so if we've got r equals c, might be something like this. That's r equals c, of course that's c. And then if this one, we do r equals a cosine theta, well, that might be something like, oh, I don't know. Sorry, I'm just trying to eyeball this a little bit here. Something like this, right? And by the way, what would this be here? Right, when theta is 0, r would be equal to a, okay? All right, and then r equals a sine theta would do something like, oh, not be so careless. I'm gonna sit up here on the y-axis somewhere, okay? All right. There are also things called cardioids and limicons. And so those have this form, a plus or minus b cosine theta, or a plus or minus b sine theta. So let's investigate which is which. Cardioid, of course, is the same root word as, you know, like cardiac or heart. So let's look at Desmos here. And I'm going to, again, play around with these. But let's add a slider B, and Yeah, we can go 0 to pi. And let's see what happens here. So right now, A and B are equal. And, oh, whoops, and we get this. Okay. Now, notice the form, A plus B cosine theta, right? This thing's oriented along the x-axis. If I had A minus B cosine theta, we'd have oriented along the negative x-axis, okay? If this A were negative, then what does it do? Oh, not much. What do you know? Now watch what happens as I play with A. So A is getting larger and larger and larger, okay? And that just is making this thing get kind of flatter, the part that makes it look like a messed up circle. But something interesting happens. Let me increase B a little bit here just to show this more detail. So I'm gonna make B equal to 3. As long as my A is larger than B, I've got this cardioid. But then, as soon as A is less than B, this thing turns in on itself. See that? That's called a limmason, okay? And so when A is less than B, we have that little internal loop. And when A is greater than B, then we have this cardioid, okay? And how is this thing traced out, right? That's another thing to think about. Like what's the, you know, as we let R, we have our, as we change theta, what does that do to R, and where does this thing start? Well, theta equals 0 is right here, right? So I could actually, I don't know if it'll let me do this. I'm just gonna see. Sine, oh, cosine theta. I can't type. No. No, bummer. Oh well. You alpha? Oh, let's see if it'll let me do this now. Alpha from 0 to 2 pi. No, bummer. Oh well. But this thing traces out over here. See where my arrow is? And it's going to come up like this, in like this, and back where it started, okay? And you can imagine if I change this from cosine to sine, what do you think it's going to do? Yeah, it's going to orient it along the y-axis, okay? So let's take a look. Maybe we can kind of play with these. So here's how this thing would trace out. It's a cardioid. Come in like this. And then like, what a horrible cardioid. I'm sorry, guys. I'm going to try that again. Sorry you have to watch me do this. To be fair, I'd be doing this poorly in class as well. I'm not the best drawer in the world. To be often, a lot of times my cardioids turned out to look more like butts than hearts. So this one's not that bad. All right. So this thing traces out in this direction. And in this case, we have A greater than B, and R is A plus B cosine theta. Okay. Now, if we had limmason here, do something like this, okay? And so we'd have A plus B sine theta, and we, in this case, would have A is less than B. So it gives us that loop in there, okay? And so cardioids and limmasons, they have that form A plus or minus B cosine or sine theta. All right, roses. These are nice. These flower-shaped deals. So let's go back to Desmos here. And I am going to leave my slider A. And we have a cosine in theta. I'm going to add a slider for n. All right, let's let n start at 1. I don't know, we'll go up to 10. Okay. So look at that. When n is 2, we have this beautiful rose here. When n is 3, we have this 3-petaled rose. And I want you to notice what's happening as I change these, right? It's kind of getting this rotation, then all of a sudden, whoop, there they go. And then when I make n 4, we have 8 petals. And when I make n 5, we have 5 petals. And so you see what's happening, right? We've got n is even, then we have 2 n petals, and if n is odd, there are n petals. And that's essentially what we get. So I'll let you play around with those. And then the last are what's known as limnoscates. And so these also have an interesting form. You could think of these as the infinity symbol. Okay, the infinity symbol. And they're going to look like, let's come back over here to Desmos. And then, so I set up this expression. And what's interesting, right, is that limnoscates have that r squared equals. And Desmos doesn't let me graph r squared. So, but notice I took a square root. And what I want you to see now is that what if I take, right, if I'm solving that, I should get a plus or minus, right? Well, watch what happens if I make this minus. It's the same curve, right? So it's this infinity symbol. And when I change this to sine instead of cosine, you can guess what's going to happen. Yeah, see, it's oriented this way. And what does A do? Well, A just elongates it, right? In either case, A is just going to elongate this thing. Okay. All right. So those are limnoscates. With all of these shapes, one of the things we're going to be doing then is finding areas, for example. So the roses, right? There are some petals, and each of those petals has an area. We can find the area in that each polar region. So that's where we'll eventually wind up. The last thing I want to do here, though, is talk about how we would get a tangent to a polar curve, right? Just like with parameterizations, right? In general, we wanted to handle those big issues in calculus. So let's talk about briefly, and I'm not going to give you an example here because I want you to take this and run with it. But I'm going to develop for you how the tangent is actually arrived at when you have a polar curve. So let's do that next real quick here. So remember, if you have a curve, right? And whoops, wrong button there. If you have a curve and we want to find, right, the equation of the tangent line. Whoa, let's actually have a line there. We want to find, we've got a curve and we want the equation of this tangent line, then we need its slope, right? And the slope is dy dx. But here's the deal. In polar coordinates, right, we know that y is r sine theta and x is r cosine theta. What you need to keep in mind, though, is that r is actually itself a function of theta. So this dy dx, I could come in here and say, okay, well, dy dx is actually, well, let's think about it. Dy would be dr d theta sine theta plus cosine theta. What did I do there? Well, it's a product rule, right? Because r is a function of theta. Similarly, oh, and I'm sorry. So this is really dy d theta, right? And then dx d theta is going to be dr d theta cosine theta minus, and then r sine theta. I'm sorry, guys, I forgot the r over here. Let me fix that. Right? Dr d theta sine theta plus r cosine theta. Okay. And so what does my dy dx become? Well, it becomes dr d theta sine theta plus r cosine theta all over dr d theta, and then where'd it go? Oh yeah, there it is. Cosine theta minus r sine theta. Okay. Whoops. Now, what's kind of nice is that if we're given r as a function of theta, you can actually go a little further with this, right? And have this all be in terms of thetas, and you won't necessarily feel that dr d theta as explicitly if you just start off by substituting with what r is in terms of theta. But this allows us an expression for finding the slope of that tangent line. And so here's the expression. Is this something you need to memorize? No, it's one of those things where you need to recognize that the slope is dy dx, and because again, slope, it's a very Cartesian concept, right? Rise, change in y, over run, change in x. So we got to get our hands on x's and y's, and we know the conversion from Cartesian to polar. And so if I know what y is equal to in polar coordinates, then I can find dy. Similarly for x and dx. And so together, I can get an expression for dy dx, which is exactly the slope I want. Okay? All right, so get your hands on all those different polar forms. I'm not going to make you memorize them all. I will tell you what it is. You know, I'll tell you what the shape is accordingly from each equation I give you. So I don't want you to worry about memorizing these so much, but you might play around with them. Spend some time graphing them. Get on Desmos, mess with values of A and B. Identify how they trace out. Right, this is all good review from pre-calc. You know, where does the cardioid begin at theta equals 0, and which direction do we trace out as theta moves from 0 to 2 pi? Okay, all those things together should be good to go. I'm ready to do some calculus. And it's the calculus that's going to come next. So we're going to look at area, and we're going to look at arc length. So get very comfortable and familiar with what those curves are, what they look like, and what their equations are. All right. So calculus next. The fun never stops.